Alright, so let's do problem number 3. Here on the left, two states. Should be immediately obvious that they are both pure shear. It's just that these are the components of pure shear. In the case on the left, happen on a plane of normals, either horizontal and vertical. And here, again, the axis would be to the, following this angle here and that as a choice. So left state, I choose my axis. Very importantly, always choose your axis. And therefore, in those components, sigma 1 is 0, sigma 2 is 0, and sigma 1 is tau 0 positive because it acts on a plane of positive normal pointing in the positive direction, or sigma 1 which acts on a plane of positive E2 and acts on a positive E1 direction, etc. Obviously not the only choice of axis, but then the matrix would change. More circle, there is no sigma, so the trace is 0 because the components are 0, and that's the key in identifying that this is a state of pure shear, because that means that the trace is going to be 0 in all axes, because once again the trace is where the center of the circle is, which is also the addition of the two normal components. Here both are 0. In other axes they are not going to be both 0, they may be negative and positive, but they're going to add up to 0. So we show a more circle here on the right. The radius is obviously the value of tau 0, can be computed using the equations. That's the more circle, and that's the point reflective of this face. For the right state, I choose axis aligned with the thing, so E1, E2 are shown in the figure. So clearly the components in those axes are exactly the same, plus tau 0 here and everything else is 0. And obviously the more circle looks exactly the same. However, they are two different states. So at this point we ask people to rotate. We ask people to see how they can be added up. Most people got this right because we insisted so much that to add components you have to add them in the same basis. So one possibility is to rotate the left state by a positive angle alpha, and I did not do that. The other possibility is to rotate the right state by a negative angle alpha there. I use the equations to show how you rotate. So you get 0 plus 0 divided by 2. For a normal stress is sigma 0 minus 0 divided by 2 cosine minus 2 alpha, and tau 0 sine of minus 2 alpha, which is minus tau 0 sine 2 alpha. Sigma 1, 2, again, use the equations, get tau 0 cosine of minus 2 alpha, but that's tau 0 cosine 2 alpha. And sigma 2 is minus tau 0 sine minus 2 alpha, which is tau 0 plus sine 2 alpha. So I draw my components in the little square, the rotated square, and I write the matrix. So now this becomes, very clear that this is a different state than the left state, because the left state is simply this little matrix up here, and here the components are those. To add them up, we just add the components, and we get this thing. So the diagonal is not modified. The shears, you get 1 plus cosine to alpha. So again, some of us cannot resist the temptation that 1 plus cosine to alpha is 2 cosine square of alpha. So we go from the double angle to the single angle. And of course we could do the same thing with sine to alpha and write it as 2 sine alpha cosine alpha. That takes us to the next question. Oops. So if you use alpha equal to 0, clearly here alpha equal to 0 would mean that the left and right states are the same, and if you add them up you will get 2 tau 0 as shown here. If alpha is equal to pi over 2, you can see that as this alpha becomes pi over 2, the top arrow is going to cancel this tau 0, the left arrow here is going to cancel that one, and so on. So you get zeros, or from the formulas. Alright, let's go to the next part. So make an argument to show that the combined state of stress is still a state of pure shear for any angle alpha, and therefore obtain the important conclusion that any combination of states of pure shear at a point result in a state of pure shear. That is really amazing. So let's see how you prove that. The main thing is that to go back to the combined state of stress here, this matrix here, or the one on the right, and to show that when you add, we compute the trace, the trace disappears. So if you were to draw more circle for this combined state, the center would be at 0. The center at 0 is a state of pure shear, period. So my argument here is exactly that the average stress remains 0, the average normal stress remains 0 after adding the states for any alpha. This is the distinctive characteristic of a state of pure shear. So what we find is that it will be pure shear. Now let's see if it will be the same state of pure shear. Of course it will not be the same state of pure shear, because we are really adding this guy and this guy. So this is going to be pure shear, but we don't know, there is going to be some angle at which there's going to be the maximum values of the shear, and we know that in those planes there will be no normal stresses because it is pure shear. I didn't go that far here because it would have been too much work, but again, when we look at this, the combined state, it doesn't look immediately like it's going to be a state of pure shear, but it is, just by adding the diagonal. And then the question is, okay, what is the maximum? I mean, what are the maximum principal stresses? What is the maximum shear, etc., etc. So the maximum shear is the radius. So we compute the radius using this formula. Let me show it here on the right. So these are the components. We do in the combined state sigma 1,1, which is minus tau 0 sine 2 alpha, minus sigma to 2, which is tau 0 sine 2 alpha, as you can see here, divided by 2 squared. Okay, it's hard to... And then plus sigma 1 2 squared, that's... I prefer to use this expression here. 2 tau 0 cosine square alpha squared. Simplify. It's clear that I get on the left I get 1 tau 0 sine 2 alpha square, because there are 2 at the numerator, so they cancel out with the 2 in the denominator. And then I can actually write the sine 2 alpha as 2 sine alpha cosine alpha all squared. So clearly I can pull out a 2 square from both. So this 2 square and that 2 square come out as a 2. Same thing with the tau 0 square, which I pulled out as a tau 0. There is a cosine alpha square here and the cosine square here. So I pull out a cosine square as a cosine, and then what I end up with inside is square root of sine square plus cosine square. I get a 1. So the new radius is 2 tau 0 cosine alpha. Many people said that the maximum shear was 2 tau 0, but that's not true. It's going to depend on alpha. It's only for alpha equal to 0, which would be, of course, this case, that the maximum shear is 2 tau 0. For any alpha, the maximum shear is going to be 2 tau 0 cosine alpha. And the principal stresses are the mean stress, average stress, 0 plus and minus r. So that's plus and minus 2 tau 0 cosine alpha. So for any alpha, the resulting state of stress is of pure shear with tau max equal to 2 tau 0 cosine alpha. The angle of maximum shear changes with alpha and is given by, so the formula here from the formula sheet, this stuff here, I replace sigma 1, which is minus tau 0 sine 2 alpha, minus sigma 2, which is tau 0 sine alpha, divided by 2 sigma 1, which is 2 tau 0 cosine square of alpha. Simplify. I get sine 2 alpha divided by 2 cosine alpha. So is this correct? That should be a square here. There is a typo. So I get 2 sine alpha cosine alpha divided by 2 cosine square of alpha, which is, then I simplify cosine and I get tangent. So I get that the tangent of 2 alpha s is equal to the tangent of alpha, which is crazy. I mean, if the tangent of alpha is equal to the tangent of beta, or tangent of A is equal to tangent of B, that means that A is equal to B, or they are apart by 2 pi, but I don't care about that. So that means that 2 alpha s is equal to alpha. That means that the maximum shear always happens at an angle equal to 1/2 of the given alpha. So if I go back here, I combine this with that, I end up with this state in my original coordinates. I now know that it's a state of pure shear. I know what the maximum shear is. I don't know now on what plane that happens, so I compute it, and it turns out that if I rotate this by an angle half alpha positive, I would end up on the planes of maximum shear. So the planes of maximum shear are exactly in the middle between these two. Of course, that's because these tau zeros are the same. If they were different, you would have a different story. Alright, I thought that this problem was incredible, very tough, very advanced conceptually, but you know, many people just followed the guide and arrived at the conclusion. So I'm very proud of you all, and we'll keep doing the good work and learning as much as possible. Thank you, everybody.